All right, so I'm going to talk today about my research on augmenting reality for people with low vision. And this talk will have a lot to do with applications of computer vision in augmented reality. Let's start by defining low vision. This is the disability that the research is going to address. So low vision is a visual impairment that can't be fully corrected with glasses or contact lenses. There are lots of different etiologies or causes for low vision. I'll show you a few very rough simulations so you can get an idea of different kinds of low vision. Here's a picture of two boys holding two balls. This is what someone with normal vision might see, or typical vision. Here's one kind of low vision that's caused by cataracts. So you would see the image is blurred and the colors are a bit off. In another type of low vision that can be caused by conditions like glaucoma, you lose your peripheral vision or your side vision. So this causes a sort of tunnel vision effect. And here's yet another cause. This is from age-related macular degeneration. Here you lose your central vision. So it becomes very difficult to see and recognize faces and also to read. And those are just a few conditions, and there are many others that cause low vision. So it's a very heterogeneous group of people. And because of that, it's been historically very difficult to design accessibility solutions for people who have low vision. There are a lot of tools that exist that can help many people with low vision. So one example is just magnification. Here's a magnifying glass. I'm sure you all have seen a magnifying glass in one shape or another. And they come in a variety of different forms. There are also many digital tools that have existed for decades. So there are vision enhancement technologies that, again, mostly magnify. They can also enhance contrast and change the colors to make text and images easier to see. And these tools come in many different platforms. You see on the left, there's a desktop solution here. In the middle, there's a handheld device. And on the right is a head-mounted display. So actually, people with low vision have been early adopters of head-mounted displays. But all of these solutions so far use these very basic vision enhancements, right? Like I said, they use magnification, contrast enhancement. This is all signal to signal, and they don't take into account what the user is trying to do. They don't take into account what the user's specific type of visual condition is. So now with recent advances in computer vision, with recent advances in augmented reality, in the hardware and software itself, in the sensors that are added to these head-mounted devices, my research question is, how can we design augmented reality visualizations that will support people with low vision in different daily tasks? So my focus here is not just on designing these simple signal-to-signal enhancements, but to take a deeper look at what people are able to perceive in different daily tasks, to try and leverage the advancing computer vision technology, and then to design visualizations that can take the results of computer vision and communicate that back to the user to support them in their task. So in this talk, I'm going to discuss the work we've done to support two specific tasks. And the first task is finding a particular product in a supermarket. The second one is navigating elevation changes. So for example, stairs and curbs, anytime there's a change in the level of the surface ahead of you when you're walking. Before I go any further, I just want to thank my collaborators in all of this work. First one here is Shiri, and she was a postdoc of mine who really helped get a lot of this research off the ground. She's currently a professor at the University of Haifa in Israel. The next here in the center is Yuhong Zhao. She's a almost graduated PhD student of mine. And Yuhong is going to be an assistant professor at the University of Wisconsin-Madison. And she's really led a lot of this work here. And then Elizabeth Kupferstein, who's a licensed optometrist who's been consulting with our group for a couple of years now and has also been very key to this work that I'm going to discuss. All right, so let's start with the first task, finding a product at the supermarket. And the first thing that we do whenever we try to design some technology for people is to first understand people's experiences and specifically the challenges that they are experiencing. To do this, we conduct a study. So in this case, we recruited 11 participants with low vision. 6 of them were women, 5 were men. And these participants arrived at our campus for a study that had a single session. So we conducted a brief interview with them. We gave them a certain task to find a product at a nearby pharmacy. And during this task, we observed them to see exactly what they did and how they completed the task. And we also asked them questions. So we tried to see not just what they were doing, but also to understand why they were doing what they were doing and what was their decision-making process. Here's the specific task that we gave them. We said, find a nearby pharmacy and buy this exact Tylenol product. So we told them we wanted Tylenol extra strength caplets, 500 milligrams, 100 count. And the motivation behind giving them this particular task was that this is something that people do. This represents the types of tasks that people do in their daily life. In order to be independent and to stay active in their communities, they need to find local businesses. They need to shop for specific products. During this task, they need to do some navigation. They need to interact with people. So we wanted to see what their experience was throughout this, what tools they used, and what specific challenges that they faced. So what we found, and I'll only give a highlight here, is that the most challenging aspect of this entire process was finding the product on the grocery store shelf. So people, for the most part, were able to find a nearby pharmacy. They were able to walk there. They were able to navigate within the pharmacy. And this wasn't without challenges, but the most difficult part was once they reached the aisle that the product was in, they had to locate the specific product on the shelf. So this involved a visual search task. This is a fundamental task that you perform all the time. There's a set of distractors or set of products on the shelf here, and you need to scan the shelf and find the particular Tylenol product in this case. There were no existing tools that they could use to do this. All of the tools we realized that people had helped them see details, but they didn't help them do this visual search task. So we decided to design an augmented reality visualization to address this particular task, this visual search task of finding a product on a grocery store shelf. So we call this QC, and QC recognizes a target product with computer vision. This is something that computer vision researchers have been working on for a very long time, for decades, locating a particular product in a grocery store scenario. Then QC will take that information, the results from the computer vision, and it'll communicate it back to the user through a set of visual cues. So these visual cues highlight the target product, and they capture the user's attention so they can locate the product. And we wanted to do this using augmented reality glasses or a head-mounted display so that the user can have this sort of augmentation in a hands-free scenario when they're walking around in a grocery store. So the key challenge for us here was to figure out how we can design these visual cues. So you could think, well, okay, no problem, this is very easy. Just put a little arrow to indicate to the user where the target product is. Okay, but then you have to remember that these are people with low vision. So if someone has tunnel vision, for example, a simple cue like an arrow is not going to be visible. If someone has some difficulty with blurred vision, then again, the arrow kind of disappears here. So it's actually very difficult to be able to understand people's perception and to design cues or any sort of visual feedback for that matter that will be fully visible and easily visible to them. So what we did here is using our knowledge of different visual conditions and going back into a bit of cognitive psychology literature, we designed a set of 5 different cues that can be combined. So I'll show you what these cues are. Here's the first one. It's called guideline, and you can see there's a red line from the center of the display to the center of the target product. Here's a cue called spotlight. So this is where we take the background, everything but the target product, change it to grayscale. Here's another cue. This is flash. So there's a frame here and it's flashing. So there's an onset effect here, which is known to attract attention when the lighter color is appearing over and over again. Here's a movement cue. Again, movement is something that's known to attract attention. And then finally, here's a sun rays cue where there are lines from around the periphery of the display converging at the target product. And like I said, you can combine these cues. So here's one example of a combination. This is sun rays and spotlight. And you can see that all of these cues have are laid over this basic enhancement here. We're also magnifying the product and increasing the contrast. And the idea behind this basic enhancement was that once the user locates the target product, we wanted them to be able to better see the details on the product so that they can verify, yes, this is the right one. We prototyped the system on video see-through head-mounted displays. So we hacked this together. This is a few years ago already, in 2016, I think. So even back then, we didn't have the types of options that we had today. So we put together an Oculus with a web camera. And here's Yuhong, my PhD student who was working on this, demonstrating how this worked. So you can see she's wearing the device. It's quite bulky, but as a prototype, it was fine, sufficient for our purposes. And you saw the cues that she's seeing on the inset here, and she's able to walk directly to the product. So for this prototype, the researcher had to indicate what the target product is. We didn't yet design the interaction where the user can indicate that. That's for another project, future work. We evaluated QC. So of course our question is, how well does this actually work for people with low vision? So we recruited low vision participants in a lab study. And we had 2 more specific questions that we wanted to answer in the study. So the first thing is that we wanted to assess the effectiveness of these different cues. So we allowed participants to try each cue and to try the magnification enhancement, which was our baseline. And they tried each cue and then they were able to select their preferred combination. The cues, as I said, could be combined, and that was done intentionally so this could accommodate participants with different types of low vision. Then we also had participants perform an actual product search task. We had them do this with 2 conditions: their preferred cues that they chose from this first part of the study, and also their best correction. So their vision as it was with the best possible correction with glasses or contact lenses or whatever it is that they typically used. And I just want to highlight some key results here. Overall, we found that QC was very effective, and all the participants preferred at least 1 cue to the baseline, which was just magnification. So what we saw here was that the cues really did help participants find the target product. So just magnifying the target is not enough to help with this visual search task. And they combined, most participants combined cues. So they combined 2 or 3 of the cues. And there was quite a bit of variation across the 12 participants. So we didn't see any strong patterns here. aside from a slight preference for the spotlight and guideline cue for the participants who had a more mild forms of low vision. When we analyzed the data for the product search task, we found that QC was faster and also more accurate than the baseline. So that was a really good finding for us. And it was about almost twice as fast as the baseline. And there were just a few mistakes that people had with the baseline, but with QC, they didn't have any mistakes. So overall, we saw that this was a very promising approach to product search. And it can also be applied to other visual search tasks. So even when you're walking around, you're constantly doing a visual search task. You're searching for obstacles ahead. So in the future, we'd like to see how we can leverage other computer vision work in other visual search contexts to create these sorts of experiences for people with low vision. That was the first task that we examined here. And then I'll talk about the next one, which is navigating elevation changes. So again, the first thing we did here was we conducted a study to understand specifically what challenges people with low vision experience when navigating the built environment. So we recruited 14 participants for this one with low vision. And again, they arrived at our campus, and we asked them to walk around certain short routes in our campus that we had set up in advance. These routes included a variety of elevation changes. And again, we observed participants throughout to understand how they behaved, why they did what they did, what tools they used, what was especially difficult for them. And we asked them questions to probe deeper into why they were doing what they were doing and what their thought process was. Let me show you some examples of the routes and the elevation changes that participants walked through. We had them walk up and down a variety of different stairs. So you can see there were some stairs here that had some more light than others, some direct sunlight. There were stairs that were just gray, plain concrete or whatever material that is, and some that were made out of wood. You can even see from this photo how challenging it is to see the stairs that are made out of hard wood here. And then we also had them walk across curbs. So they crossed a street, and we had them walk across different surfaces. In some cases, there was only the perception of an elevation change here where there was a change in surface. So what we found was that walking up and down stairs was the most challenging task for participants. And many people with visual impairments used a cane, but mostly those are people with little to no vision. So in our case, we saw that only 3 used a white cane, since our low vision participants did have some vision that they used. So 11 didn't use any tools, even though what was interesting here is that 6 of them actually had a cane with them, but they said that they didn't use it. So when walking up and down stairs, they walked very slowly, they paused a lot, and we saw that they looked down a lot. They had to stare down at the stairs to really try and see the elevation changes, and they shuffled their feet to try and get that tactile feedback, and they also held on to the railing. So to address this, we designed a visualization called Stair Light, and Stair Light, again, it uses computer vision to recognize stairs. And then we take that information, we try and communicate it back to the user, and we present visual and also some audio cues here to direct the user's attention to the presence of the stairs, and also so the fact that there are stairs coming up, and also to enhance the visibility of the stairs themselves, so to enhance the edges of the stairs. And in this case, we didn't use a head-mounted display, we used a projection-based system, so we can add the visualizations directly to the environment.
Shiri, just a heads up, 5 minutes remaining.
Okay, so I'll show you the setup here really quick. So in the future, there'll be projection available on smartphones. There's already a trend towards that direction, but we set up a mock-up here with stationary projectors. So here's a demonstration of our visualization. So you can see that in this case, we had some yellow highlights at the edge of the stairs. Here's one example. And again, the question was, how can we best communicate these to attract people's attention? So we experimented with different animations here. So here are a couple. We had some horizontal and vertical zebra stripes here. Here are the vertical zebra stripes. And we also looked at what was the most effective way to highlight the middle stairs, which were a little less important. So these didn't need to attract people's attention quite as much. We looked at blue highlights and also yellow, dull yellow highlights here. So again, we conducted an evaluation with people with low vision to assess the different forms of the visualization and also to see how our system performed in a stair walking task. To highlight just the key results, in this case, we saw that most participants preferred just the basic visualizations with no animations because they found the animations distracting. And we found that our system helped people walk faster. There was a trend towards that. And subjectively, they felt that having these visualizations really helped them feel more secure as they were walking up and down the stairs. And they felt it would be especially useful in the dark. So moving forward, there are lots of questions here, and I'll highlight just a few. We saw that there are many different types of low vision, and it was hard to predict which cues would be best. So one of the things that we think are key here is to optimize customization, whether this is inferred automatically through the system or whether we allow the user to adjust this is one question. And we looked primarily at visual augmentation, but there are also ways of providing audio and tactile feedback in augmented reality as well. So that's another area for future work. And of course, we want to be able to evaluate these systems in the real world eventually. So we need reliable computer vision for that and more usable, so lighter and better battery life, et cetera, for the hardware devices. So we want to be able to evaluate the perception and behavior using these visualizations. So just to conclude quickly, one important parallel to this work is making sure that the actual devices themselves, the AR and VR platforms, are accessible. And I want to note that we have started an initiative along these lines to achieve this goal, the XR Access Initiative. And a plug, we have our annual symposium coming up in late July. So you can check out xraccess.org if you're interested in that. So just to summarize, I talked about low vision, which is a very common and understudied disability where people do have some functional vision, but it can't be fully corrected with any existing tools or medical procedures. And I showed you two applications, two types of visualizations where we leverage some computer vision technology to enhance the user's perception in a certain task. So there was QC, where we augmented people's environment for finding products in a grocery store shelf, and Stair Light, where we added augmentations to stairs to help people navigate more effectively. And I'm happy to take any questions. Thanks very much.